we're going to take a look at horizontal asymptotes, and you're like, what? I can barely even do vertical asymptotes. Okay, horizontal asymptotes are actually pretty easy. Remember, a horizontal asymptote just tells us the end behavior of a function. It tells us when x is a really, really big negative number, what's going on, or when x is a really, really big positive number, what's going on. So the limit as x approaches negative infinity, or the limit as x approaches infinity. So we're just looking at those two things. So for these horizontal asymptotes, we're going to look at this function. And one of three things can happen. Either you have a slant asymptote, which means it's not like a straight line, it's just this like random line. Not random, it's a line. Or you have a horizontal asymptote of 0, or you have a horizontal asymptote of some number. So let's just reason our way into this for a moment. When I have something like this, let's remember we're putting in a huge number, okay? And when I put a huge number in here, let's just think about what happens. When I take a huge number and I square it, and then I add a huge number and subtract 9 from it, do you think this 2x and minus 9 actually matter in the scheme of things? No, absolutely not. Because if I take like 1 million and I square it, that's a huge number. If I took 1 trillion and I squared it, it's so huge that adding or subtracting 9 from it, or even adding another million to it, doesn't even matter. So the interesting thing about horizontal asymptotes is when we're looking at horizontal asymptotes, we only care about the biggest factor, not the biggest factor, excuse me, the biggest term in our equation. So same thing here on the bottom. If I put a huge number and then there subtract 9, nobody cares about that little 9, right? So all I'm looking at is the biggest term. So let's imagine what's happening when I'm looking at this. Well, really, this basically behaves like x squared over x. It doesn't, I'm not going to put an equal sign there because it isn't equal to. It just behaves like x squared over x. Well, what is x squared over x? That's just x, right? So what is going on in this function when I put a huge number in here? Well, I get out a huge number, right? If I put a huge number into this, I get out another huge number, okay? So for this one, it doesn't approach a specific number. It keeps getting huge, right? And so this has what we call a slant asymptote because it actually, if you look at it, the limit as x approaches infinity of this function, if I put a huge number in, I get out a huge number. So the limit as x approaches infinity is infinity. So this has what we call a slant asymptote. So it approaches a line, but not a horizontal line. It doesn't approach one value. It just keeps on getting bigger and bigger toward infinity. So then let's take a look at this next one. Remember, we only care about the biggest terms in each of these, so nobody cares about this and nobody cares about that, because when we get to huge numbers, they're so tiny that they don't matter. So really this behaves like x over, oh, I should not put an equal sign there. It behaves like x over x squared, which is the same as 1 over x, right? Well, let's think about what's happening when I put a huge, 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 huge number into 1 over x. Well, I get 1 divided by a million. Well, that becomes basically 0, right? 1 divided by a huge number is 0. So the limit as x approaches infinity of this function, we can say of 1 over x, is 0, right? Because if I put huge numbers in here, I get 0 out. And I'm getting really close to 0. Even if I put huge negative numbers in here, I'm still going to be approaching 0 because it's going to be 1 divided by a huge negative number, so it's just almost 0. So in this case, we have a horizontal asymptote at y equals 0. Okay, our final option is something like this. Let's see what's going on here. Again, we don't care about all of this and we don't care about all of that because they don't matter in the scheme of things. Only our largest term matters. So this is growing. This is very similar to x squared over 2x squared. And so then we look at that and we say, all right, what does that actually behave like? Well, that actually just behaves like 1/2, right? Because x squared divided by x squared. You know, because if this is growing at a huge number, say this is 1,000,000. Well, 1,000,000 squared divided by 1,000,000 squared is 1, right? A huge number divided by itself is just 1, right? So they basically cancel each other out. And all we're left with is the coefficients in the front. Because all of these other numbers basically just cancel each other out, okay? So when you have something like this top and bottom are growing basically at the same rate, right? This is 1,000,000 squared over 2 times 1,000,000 squared. Well, 1,000,000 squared divided by 1,000,000 squared is 1. So then it's times 1/2. So do you see a pattern with our horizontal asymptotes? We have 3 different options. If the top degree is greater than the bottom degree, that's the first one, then we have a slant asymptote. And when we have a slant asymptote, that means that the limit as x approaches infinity of the function is infinity or negative infinity. And to find the slant asymptote, we're actually going to use long division to find where that slant asymptote is. If the top degree is less than the bottom degree, like that second example, then we have a horizontal asymptote. And the horizontal asymptote, oh, that's the second example, not the last one. Sorry, if the top degree is less than the bottom degree, yes. So if the bottom degree is greater, it's growing faster, right? And what are we going to do? We're going to have a horizontal asymptote at x equals 0 because the bottom is growing so fast that eventually you just get 1 divided by a huge number, which is 0. If the top degree is equal to the bottom degree, then we have that last example. So we have a horizontal asymptote. And the horizontal asymptote is going to be, you're going to take the leading coefficient of the top divided by the leading coefficient of the bottom, like you saw in our last example. And that doesn't want to write for me. So basically, remember, the top and bottom are going at the same speed, so we just end up with the leading coefficient over leading coefficient.